Welcome to the new video. This one's on the periodic table. So let's get started. So here's the periodic table unit. We have already been using the periodic table and you've got to figure out different pieces and parts of it. And that's all well and good. But now we're going to get into a little more detail of the history and the inner workings of the periodic table and really find out that this is a magical system that just makes a lot of sense. And hopefully you guys will enjoy it just as much as I do. So here we go. We have to talk about early scientists, okay? So there are many scientists that have worked in the periodic table. In fact, new elements are being discovered at this time, even today. There are new elements that are being discovered as we humans use a particle accelerator, electron colander, and we are just creating atoms. So we're just adding more and more protons and creating brand new elements, which is kind of cool. These elements, though, they're only really in existence they only really exist for a short amount of time, and then they just kind of disappear. So not really disappear, but they break down into other more stable elements. So the question is, the ultimate question is, are they really even considered elements or not? And that's really to be determined, not by us, but by the powers that be. And as you can see on your periodic table, the UUUs and things that don't have an official name, those are the elements that we are discussing that just blimp into existence just for a couple of seconds, and then that's it. So I think they're still, of course, determining what names to give these things if they are really considered an element, even though they're not that stable at all. Okay, so guy we need to talk about, though, is this Russian guy, Dmitry Mendeleev. Okay, pretty cool. He invented the periodic table, so you can thank him for the thing that you're looking at and on your reference tables. He organized the elements by properties, so how they behave, what about them. All right, he arranged the elements by atomic mass, and he was able to, using his system, he actually was able to predict the existence of elements that were not known to anybody at the time. Okay, so element 101 is named after him, so you guys can kind of take a look at that. Element 101. Okay, so here is his system. It's all written in Russian, and it if you take the time to kind of look at it, kind of makes sense. Hydrogen's number 1, lithium's number 7. Okay, all right. So you're going through this, and you see that he took the time to kind of figure out how the system worked. All right. So here again is periodic table. The purple are holes he was able to figure out. Didn't know what elements go there, but he was able to say that there should be somebody here. There should be somebody over here, for example. All right, Moseley. Okay, this guy was great. Determine the atomic numbers of elements from the X-ray spectroscopy, basically, in 1914. So he arranged the elements by increasing atomic number, which is how it's arranged today. So this is, of course, our modern periodic table. So thank you, Moseley, for that. So here, this is our periodic table. They are arranged according to Moseley's system, not by Mendeleev, but Mendeleev got us basically to Moseley, switching it around, and here we are today. So increasing order of atomic number. So 1, 2, 3, 4. They're going in order, okay? And you guys could take a look. Recall the atomic number is the number of protons in the nucleus. So hydrogen, number 1. He was number 1. Helium, number 2. He's got 2 protons. Lithium, 3, etc. And they're all put in order perfectly down to the T. Okay, so metals and nonmetals. We had talked previously when we talked about ions about the metals being losers, the nonmetals being gainers. And I showed you that last picture of the periodic table having your cations over here, the metal section, and your anions, the negative guys, over here. So it's a little prelude there that the metals are here, the nonmetals are there. We have this section of basically weird guys, if you want to call them that. These are your metalloids, and they have properties of both metals and nonmetals. And they're right here in the area in which I call the boron staircase, because you're starting with boron. Don't be a moron and forget about boron. and you're dropping down with this beautiful staircase pattern, and the guys that are in and around the staircase, those are what we call your metalloids. Okay, other places may call this just a zigzag line, and that's cool, but you need to remember the importance of this zigzag line or staircase, that these are where your metalloids are going to hang out. Okay, all right, so a metal, you guys know what a metal is, all right? It's pretty much at this point common sense. But let's explain it on a chemistry level. Metals are solids at room temperature, aside from mercury, which is your only weird one, that's a liquid. The most reactive metals, so the ones that are really nasty, are going to be found in groups 1 and group 2. All right, so periodic table, group 1, it goes up and down. Groups are like columns. And group 2. Okay, so these two groups are pretty violent. Okay, group 1 more so than 2. Properties of a metal. Metals conduct heat and electricity. Okay, this is due to the fact that their valence electrons are mobile. They can move. Okay, because the electrons can move, the electricity can flow. If the electrons cannot move, the electricity cannot flow. There's a very, very, very simple way to understand this if you want to know a little bit more about electricity. And I know this may seem very juvenile, but I guarantee you it's worth your time. If you would like to, you could watch the episode of the Magic School Bus. The time when Miss Frizzle, when the bell does not work, and they talk about in the episode, they talk about electricity and the flow of the particles, which you guys are now advanced chemistry students, are learning that the particle that they're referring to is electrons. So the flow of the electrons, and if the flow stops, so say you cut that wire, for example, and the flow stops, the electricity is not going to be transmitted. The electrons are not going to be able to move. They can't jump over the cut wire. So, of course, the whatever it is that you were trying to plug in, whatever electronic device it is not, it's not going to work. Okay, so again, if you wanted to take the time, watch that episode of the Magic School Bus. It's a very, very easy way, I feel, for you guys to understand just the idea of electricity. So anyway, metals conduct heat and electricity. Your pots and pans are made out of metals. The wires that you use to plug in everyday devices, underneath that rubber outside coating, it's all metal. Metals are malleable. They can be hammered into shapes. And metals are ductile. They can be drawn in or pulled into wire. So they can be drawn to make wire. All right, more properties of metals. Metals have a luster. They're shiny. Metals have a low ionization energy, which basically means they are losers and they lose electrons. And we knew this already. And if you don't know or don't remember, you should remember that your ionization energy, your first ionization energies, are listed on table S in your reference tables. So if you're ever asked to compare the ionization energies of an element, of any elements, metals, non-metals, whichever elements they give you, you just take a look at that data on table S in the reference tables. Metals have a low electronegativity, which is also going to be located on your table S in your reference tables. So if you don't know, you don't need to memorize it, but you do need to know, however, what electronegativity means. And that means that they basically, again, they want to lose electrons. So it goes hand in hand. Low electronegativity, they want to lose those electrons. High electronegativity, they want to gain those electrons. Okay? All right. So what's this mean about a metal and its electrons? It wants to lose them. That's what it means. Okay? It's exactly what it means. It wants to lose them. Non-metals, though, on the other hand, non-metals can be gases, solids, or liquids. The only liquid that's a non-metal is bromine. And that means we only have 2 liquids at all on the periodic table. Mercury is your metal. Bromine is your non-metal liquid. Okay, nonmetals are brittle. They are not ductile. They are not malleable. They are not a metal. They are non-metal. Nonmetals are dull. They lack a luster. They are poor conductors of heat and electricity. That's your non-metal. Okay. Nonmetals have a high ionization energy. If your metals want to lose, your nonmetals want to gain. So they have a high ionization energy, high electronegativity. What does that mean? They want to gain electrons. They want to become ions with a larger atomic radius. They want to be, they are what we consider an anion, and because they want to gain electrons. It's just much easier for them to gain than it is for them to lose, mainly because of what's on their valence shells. These nonmetals tend to have larger amount of electrons in their valence shells. Not 8 yet, but larger, say 3 or more, because it makes more sense for them to gain the remainder than to just lose what they have. All right, your metalloids are semimetals. These guys are the ones around that boron staircase, that zigzag line. So they're between the metals and the nonmetals. They have both properties of metals and nonmetals. Metallic refers to metal, non-metallic, nonmetal. All right, so these are your list of your metalloids. And there's a beautiful diagram, basically showing you color coordinating where everything is. So purples are your metals. Take a look at how many purples you have. Yellows are your nonmetals, and note the yellow guy over here. This is hydrogen. He's a little bit in an odd situation. He's not with his friends, and that kind of makes sense if you realize what group he's in. He's in group 1 with 1 valence electron. All right. So, and then your blues are your metalloids, or your semi-metals.